Alrighty, in this video we're going to be talking about how vectors can be added and subtracted and what vector addition and subtraction looks like graphically, as well as some examples of real-world problems that vector addition and subtraction can be used to solve. So vectors are added what we call component-wise. And when we talk about an operation being component-wise, we're talking about if you want to add two vectors, you add the x components, then you add the y components, and then if you have z components, you add those too. So for example, if someone is asking me to add the vectors 3, -1, 2, and 5, 1, -4, then I would just add together the x components of the vectors 3 plus 5. Separately, I would add together the y components of the vectors -1 plus 1. And then separately, I would add together the z components of these vectors. So that would be 2 and then plus -4. So simplifying each individual component gives me an answer of 8, 0, and -2. Now, vector addition can be understood graphically using something called the triangle rule. And to demonstrate the triangle rule, let me do some vector addition using some really simple vectors that are easy to draw and picture. For example, let me add together the two vectors 1, 0 and 0, 2. So let me nickname the first vector by the notation v. And what you're going to see me do is you're going to see me write this letter v with an arrow on top of it. When we write a letter with an arrow on top of it, that's a way of communicating and emphasizing that the quantity that we're writing down is a vector as opposed to a scalar. Let me nickname this first vector v, and let me nickname this second vector w, also denoted with a little vector arrow on top. Now, I'll start in the xy plane by drawing the vector v, and I'm going to draw it in standard position from the origin. So the vector v would be pointing 1 unit straight out to the right, 1 unit in the positive x direction. I'm now going to draw the vector w, but I'm not going to draw the vector w from the origin. Instead, I'm going to draw the vector w from the arrowhead of v that I just marked down. So from the arrowhead of v, I'm going to move 2 units in the positive y direction to represent the vector w equals 0, 2. Now let me add these two vectors together and let me make sense of that sum within this picture. If I add together the vectors v and w component-wise, then the result is going to be 1 plus 0, 0 plus 2. It's going to be the vector 1, 2. And if I draw this vector emanating from the origin, look what happens. If I draw this vector emanating from the origin, it forms the final side of a triangle. A triangle with one side v, another side w, and then this third side becomes the sum v plus w. So these three vectors, v, w, and v plus w, form a triangle. Another way to understand this, you can think about v plus w as taking first the path v and following that vector forward, and subsequently taking the vector w and following that vector's direction. And then where you end up as a result of taking v first and then traversing w, the shortcut from start to finish is the vector v plus w. So another way to sort of express this same situation is that if you have a vector v that's taking you from a point A to a point B, and then you have a vector w that's taking you from that point B to a point C, then the sum v plus w takes you directly from the starting point A to the final point C. So it's basically a shortcut that eliminates this intermediate position B within this drawing. Let's do another example of the triangle rule with two other vectors. So let me call this first vector v being -1, 2. Let me call this second vector w being 1, 1. Let me draw these vectors together on the xy plane. I'll start by drawing v emanating from the origin. So v emanating from the origin would be 1 unit in the negative x direction and 2 units straight up. So v would be coming in like this. Then from that position, I'm going to traverse the vector w. So I'm going to start the vector w here, and then I'm going to go 1 unit to the right, and then 1 unit up. So the vector w would take me right here. Now let's add these vectors together and make sense of the sum within this picture. V plus w would be -1 plus 1, 0. 2 plus 1, 3. So that would be a vector that points 3 units straight up. If I draw that vector from the origin, once again I see that it forms the final side of a triangle that has one side v, another side w, and then the final side is v plus w. Alternatively, I can think about this as traversing two paths back to back. First, the vector v takes me from an initial point A to an intermediate point B. W takes me from that point B toward a final point C. The sum v plus w is basically just the shortcut that takes me directly from point A to point C. To summarize this rule, I could say something like the following. Draw v anywhere. Then draw w from the head of v. The sum v plus w connects the tail of v to the head of w, forming a triangle. Triangle rule for vector addition. So this is how we understand vector addition graphically. In terms of physical applications, vector addition can be used to calculate, for example, net force. And in physics, when we talk about net force is equal to the sum of all the vectors that are acting on an object at the same time, representing what all of those forces do together in total to the object. So let's use vector addition to calculate net force in, for example, the following scenario. We've got a 5 kilogram object in 3-dimensional space, and two forces are acting upon it. First is gravitational force, and second is a force being imposed by a wind blowing in the negative x direction, a force of wind with a magnitude of 3 Newton. If this is the landscape, let's go ahead and find the net force representing all the forces acting together on the object at the same time. So the first thing that I'm going to do is I'm going to take the two forces that are described to me in this problem, and I'm going to calculate the vectors representing those forces. I'll call F1 the force of gravity. And I'll call F2 the force from this wind. Now, as I'm calculating gravity, I'm going to remember that the direction of gravitational force is straight down, which in our case, in a 3-dimensional problem, is going to be in the negative z direction. I'm also going to remember that the magnitude of gravitational force can be calculated using that formula, the mass of the object times the constant g, which we take as 9.8 unless otherwise stated. So in our case, the mass of the object is 5 kilograms, the constant g is 9.8, so the magnitude of gravitational force is going to be 49 units for this object. So if I express gravitational force in its component form, I would get a vector that has nothing happening in the x direction, 0 for the y component, and then the entire magnitude is stacked in the negative z direction, 49 units applied straight down. Then we have the force of wind, and we're told that the wind is blowing in the negative x direction. So that's the direction along which this force is applied. We're also told the magnitude of this force directly. We're told that the magnitude is 3 Newton. So if I use this data to write this vector in component form, this vector would become negative 3, 0, 0. So the net force would just be the sum of the forces acting on the object, the sum of F1 and F2. So that would be 0, 0, negative 49, negative 3, 0, 0. So that gives me negative 3 in the x component, 0 in the y component, and negative 49 in the z component. So this would be the net force acting on this object in this scenario. Vector addition can also be used to make sense of taking two displacements or multiple displacements and traversing them in sequence. To give you an example of that kind of calculation, suppose we have an object that starts at the origin. Then it follows this displacement vector, negative 2, 4. Then it follows this displacement vector 3 minus 1. Then it follows 0 minus 5. Where is the object positioned in the end? So if I start, for example, at the origin, and I then traverse the first vector, negative 2, 4, that's going to take me to some intermediate point A. If I then traverse the second vector, 3 minus 1, that's going to take me to some other intermediate point B. If I then traverse the final vector, 0, negative 5, that's going to take me to some final point C. And so if I want to know where I have ended up as a result of taking these 3 steps back to back, I can use the same kind of principle that we used earlier when we were doing triangle rule. If I have a vector v that's taking me from point A to point B, and if I have a vector w that's taking me from point B to point Z, then the sum v plus w will take me directly from A to C. And we can apply that same principle here. If I want to figure out what vector is going to take me directly from the origin to the final point C, all I have to do is add these 3 vectors together. So I'll add together the vector negative 2, 4 with the vector 3 minus 1 with the vector 0 minus 5. If I add the x components, that's negative 1, positive 3, 0, so that's positive 1. If I add the y components, that's 4, negative 1, negative 5, so that's negative 2. So that's a vector that points 1 unit in the x direction and 2 units in the negative y direction, which is consistent with what we would predict from our little sketch. So if we now think about this in terms of the object's final position, we can see that this vector is pointing to the location in the xy plane, parenthesis, minus 2. The location of point C, the location of the arrowhead that we see as we draw this vector from the origin. So this would be my final position if I start at the origin and then follow these 3 movements. I can find that just by adding the displacement vectors together. Now, vector subtraction, just like vector addition, is performed component-wise. So if someone gives me, for example, 3 minus 1, 2, and then subtract 5, 1, negative 4, then I can do that by just taking 3 minus 1 and 2 and respectively subtracting 5, subtract 1, subtract negative 4. So the difference between these two vectors after simplification would be negative 2. It would be negative 2 again, and then it would be positive 6. That would be the difference between these two vectors. Now, just like vector addition, vector subtraction has lots of real-world applications. And primarily, vector subtraction is used when you're solving equations containing vectors. For example, consider the following scenario. An 8-kilogram object in two-dimensional space being acted upon by gravity as well as some other force that we don't know yet. We do know that the net force acting on this object can be represented using the vector negative 2, 1. So let's try and use this information to figure out what this other mystery force must be doing. Now, the first thing that I'm going to do is I'm going to recognize that I can find the gravitational force vector pretty easily using the same technique that we've used earlier. I can calculate the magnitude of gravitational force by multiplying the object's mass with this constant g. In our case, the mass is 8, and assuming standard conditions, the g is 9.8. So the magnitude of gravitational force here is going to be 78.4. We also know that the force of gravity acts straight down in standard conditions. And in two-dimensional space, straight down is the negative y direction. So that means the force of gravity as a vector would be equal to 0 in the x component and negative 78.4 in the y component, the entire magnitude showing up in the negative y direction. Now, meanwhile, we have this other mystery force that we don't know yet. This other mystery force that we're trying to calculate. But if we did know that force, we could calculate the net force by adding these two together. The net force would be equal to the sum of the force of gravity and the other mystery force. So, knowing the force of gravity, we can fill that in. We don't know F2, but we actually are given the net force on the other side of the equation. The net force is given by this vector negative 2, 1. So now we can actually take this vector equation and solve it for F2 by subtracting the force of gravity from both sides. If I follow through on this component-wise subtraction, I get in the x component negative 2 minus 0, and the y component 1 minus negative 78.4. So that's 1 plus 78.4, giving me 79.4. For another example of this at play, let's do several different triangle rule type problems. We have two solid vectors, v and w. And we're going to try and express this dash vector in terms of the two solid vectors that are given. So for example, here I have a vector v extending from an initial point, maybe call it A, to an intermediate point, maybe call it B. And then w is extending from B to a final point C. Meanwhile, the dashed vector takes us from A to C directly. So if I call the dashed vector x, I can understand x using the triangle rule directly. By the triangle rule, x is just equal to v plus w, the sum of these two vectors. However, let's consider what happens if we switch up the diagram a little bit. Now, as I look in this picture, I find that the vector w and the vector x are now the two vectors that can be traversed back to back. If I start over here at point A and I follow w to an intermediate point B, I can then follow the dash vector x to a final point C. And then v is the vector that takes me from A to C directly. What this means is that by triangle rule, the vector v is equal to the sum of x and w, because you can follow w and then you can follow x, and then v would be the shortcut for that path. Now that I've set up this equation, I can solve it for x, and I can express x as the difference v minus w. For another example, this is a drawing we're going to see again later in a few lessons. And what I notice as I analyze this picture is that from this initial point A, I can follow the vector v to this intermediate point, and then I can follow the dashed vector to this final point. And then w will represent the direct path from point A to point C. So if I use triangle rule, that means that w is equivalent to the sum of v and x. If I take v and x back to back, the result is the exact same thing as w. So solving this for x, I find that x is equal to w minus v, the difference in the other order. So this concludes our lesson on vector addition and subtraction. Vector addition and subtraction is done component-wise, which means add your x components, add your y components, and add your z components. Vector addition can be understood graphically using something called the triangle rule. If you're trying to get a graphical interpretation of something like v plus w, start by drawing your vector v as emanating from some original point, taking you from an original point A to an intermediate point B. Then draw your secondary vector w from that position, taking you from the point B to a final point C. The sum, v plus w, will take you from A to C directly, forming a triangular picture from these three vectors. Vector addition can be used to calculate net forces. It can also be used to make sense of taking several displacements and several movements back to back. And vector subtraction can be used to solve vector equations involving addition.